for the previous section because I cancelled class yesterday. So I will share this video with them. Okay, so you just focus on something like that. So, okay, so we are going to continue the surface charge. Okay, based on the Gauss Law. Okay, so give me some time. I need to draw my surface. So you can draw yourself the surface also. This is a surface. Okay, so we have a surface, infinite size surface, which means that this is extend to positive infinity, and this one is extend to negative infinity, as well as y. Okay, positive infinity and negative infinity. Very big side of planar. Okay, and as you know, for the surface charge, you have many charge on the surface. Okay, and usually we will be given the rho s. So this is how we illustrate the surface charge in 3D. Okay, besides 3D, we can also illustrate the surface charge in 2D, right? So in our previous calculations, we only draw the diagram in 2D because that is easier for us to analyze, right? So if you draw your planar in 2D, okay, you can get something like this, right? So this one is your axis Z. Okay, this one can be Y and can be X. Okay, no matter it is Y or X, you will see the same thing, right? So you have many charge. Okay. On the surface, huh? So usually the question, you have tried so many questions related to the surface charge. We need to find the electric field intensity, sometimes here, right? Sometimes here, here or here. Am I right? It is either up or down. So by using the Gauss Law, the first thing we have to do when we want to calculate or derive the formulation for electric field is we must construct a Gaussian surface. Okay, so this Gaussian surface, it must touch the observation point. Okay, so you can construct the Gaussian surface. So this is the Gaussian surface. So this Gaussian surface, as I mentioned, it must touch the point where we want to know is electric field intensity. So it will be something like this. Okay, so I label here as Gaussian surface. Okay, so the second step is we move on to the formulation for Gauss Law. Okay, this is the formulation for Gauss Law, right? Okay, which means that, okay, if we integrate the flux coming out from the surface that enclose the charge, can find the total Q, which is enclosed by the surface. Okay, this is the definition by using wording. But if using mathematical equation, this will be the equation to represent the Gauss Law. Okay, so we look at this. S is a surface, right? So we have to refer to your Gaussian surface here. So how many surface that you have? 1, 2, 3, 4. Right? So you have 4 surface. So meaning that for this mathematical part, you have to find out the integration from the top plus the bottom, and plus the side. Okay, you have left side and you also have right side. Right, then only we can get the total Q. Okay, total Q. Look at here, this case. So this is an infinite plane. Okay, we assume there are positive charges on this plane. In your opinion, what will be is the direction of its electric field? For this side, it will be pointing in the positive Z direction, right? Okay, so for the bottom side, it will be pointing towards the negative Z direction. How about the side? This part. This thing, it is extended to infinity, right? Meaning that there is no electric field coming out from here. Am I right?
Yes.
No this thing, no such thing. Okay, so it means that the flux that is coming out, okay, from the left side and also right side, they will be equals to 0. Okay, so we only focus on the integrations of top and also bottom. Okay, you clear? Okay, we move on to the top. We look at the top first. So top, we have this one. Okay, we have D. Okay, so we have to refer back to our Gaussian surface, the top Gaussian surface. So where is the direction of my electric flux density? Positive Z. Am I right? So here you label it as Z, the directions. After that, you have a dot product, ds. So what ds you want to have? Dx. What ds you want to have? So you have to refer to this one, right? So which one you want to use? You have Cartesian, you have cylindrical, you have spherical. So Cartesian. So why you decide you want to use Cartesian? Because of the shape of your planar, right? This is a rectangular planar. So you will use this one. So there are 3. Which one you want to choose? Z. Okay, in the direction ZY. So you look at your Gaussian surface. This is your surface, and this surface, it will form a 90 degrees angle, okay, in the direction of Z. Am I right?
Yeah.
So that's why you will choose Z. Okay, so here when you choose Z, here will be dx dy or dy dx, right? So here you have another Z. On the right hand side, initially we have Q, right?
Yeah.
But this surface, they didn't give you the Q. They give you the rho S, surface charge density. So it means that if you want to get the Q, you have to integrate the surface charge density again is ds, right? But this ds don't have direction. If you still remember, this ds don't have direction, right? It's like this. Okay, rho S ds. No direction. Okay, but this one is a quantity that has direction. Different things. So here we'll put ds, then we will use the ds dy. Okay? So you need to define the interval for your dx dy. Okay, so your dx, this is your x, this is your y. Because it is an infinite plane, so the size will be infinity, right? So you from negative infinity to positive infinity. Okay, infinity, infinity. Okay? Okay. Here, same thing also. Okay, infinity. Okay, infinity. Okay, so we expand the integration. Okay, first of all, we need to settle this unit vector. Okay, both of them, they are in same direction, right? So it will be equals to 1. Not 0, 0, the whole thing 0. Okay, 1. So when 1, then this one, it will be d. Okay, when you perform this one will be right, infinity, right? And this one also infinity, infinity, right? This one also rho s infinity plus infinity, and this one you have infinity plus infinity. Right, am I right? So here I will cancel out the things. Each are the same. Infinity, right? We don't know the value. So your D is equivalent to rho s. Rho s, Is it correct?
Yes.
Now you can specify its direction is positive z direction. So this is for the top surface, right? Any idea for the bottom surface? Same, right? So I no need to perform this operation anymore. So for the bottom surface, you will get the same things. Okay? Rho x, but in the negative z directions. Okay? So the total flux, okay, total, it will be the summation of the flux coming out from the top and the flux coming out from the bottom. Okay? This is different direction. Let me refer to this one. Plus the rho x. Okay, this is for the bottom. This is just the directions. Okay, so you have 2 rho x. Okay, this part, okay, if you look at this one, it means that I have to add the surface integral from the top and also bottom together, then only I equivalent with the Q, right? So I cannot do it in this way. Okay, so which means that this one no, this part lah. No, this part first, Otherwise you will confuse like me. Okay, so we continue this one. So no cancel out. So no cancel out. Okay, plus this thing, right? Right. So here you will have D. This one multiply this one, it will be. Okay, if I represent this one with L, okay, the symbol, just a symbol. So here I will have L squared, right? So for the bottom part, I will also have dl square, right? L is actually just a variable because writing this one is too long, right? So I just represent this one to be equivalent to L, and also this one is L, so you will have L square. And for the bottom part, you will have L square also. So the total flux, okay, on the left hand side will be dl square, right, plus the dl square. So you will have 2 dl square. Okay. Okay. So this is at this side. Okay. How about this side? Q. So actually just now we have tried the Q, right? Q is equivalent to your integration from infinity, negative infinity to positive infinity, the surface charge density ds dy. Right? So just now we mentioned the answer is rho s. infinity plus infinity, okay? Multiply infinity plus infinity. So this one I represent it as L as well. So rho x, I will have L squared. So now left hand side, I will have this one, okay? And left hand side and right hand side will have this one. So I put them together. D2L squared equivalent to rho x L squared. Then only I can cancel out. If I cancel out too early like just now, right? I cannot get the equations. Okay, this one. So this will be a D rho s over 2 over 2. Right? Over 2. And the direction is, it can be positive or negative, right? Okay, depends on the place where you want to determine its electric field. So in the slide, they put it as a n, unit vector n. But for this case, we can put it as a unit vector z. Okay, for our planar. Okay, and for the E, right? It will be rho x over 2 epsilon naught. So from the D, we can get the E. Why? Because of this relationship. So this relationship you should bear in your mind. You don't forget it. So after you get the D, you get the E. So we get the same equation as what we have learned from the Coulomb's law. Any questions? No. So boring. You already know all these equations, right? Why you need to rederive again? So actually all this is just a practice for you. Because in some of the question, you might need to rederive again. Okay, you will not use the same equation here. Depends on the situation. Okay? Clear? Clear? So we move on to the last structure here. In Coulomb's law, we didn't derive any formulation for volume structure because this is very complex. And now we are going to use the Gauss law to derive the electric field intensity when there is a structure given their rho v. Okay, volume charge density. Okay, how to find its electric field intensity. Okay, we'll focus this one. So, okay, now imagine you have a spherical volume. Okay, spherical volume. Okay, I will draw it here under the section volume charge. Volume charge and Gauss law. Now imagine you have a very big sphere. Okay, you have been given the rho v. Okay, so let me draw the coordinate system, might be easier for you. Okay, you have a sphere. So this is your sphere. Okay, given the rho v, and you have to find the electric field somewhere here. Any point here? Can be here, can be here, can be here. Or find the electric field outside the sphere. So what kind of formulation that you have to use? We didn't use this formulation, or we didn't derive for this formulation by using the Coulomb's law, right? Now we are going to derive it using Gauss law. So by using Gauss law, you can determine the electric field intensity at all these dotted points. Okay, so this is the center of your sphere. This will be R. Okay, now let's look at the condition when the R, this one is the radius of the sphere. When the R, the location that you want to find its electric field is less than A. What does it mean? R is the location. For example, from here to here, okay, is R, okay? And from here to here can be R also. So the R, the location of the R is less than the value of the radius, okay? The radius of a sphere. So it means, what if now you want to find the electric field within the sphere? What you have to do? Okay? So again, you should start from constructing the Gaussian surface. If this is the point that you want to find is electric field, so you construct a Gaussian surface. Can you see this dotted line? So this dotted line actually represent the Gaussian surface. Okay, so you construct the Gaussian surface. After that, you come to the same equation again. Okay, it is always started from this equation because this is the basic of Gauss Law. So after that, what you should do? Okay, give it the roll. Okay, now specify the direction of the flux. Okay, if the whole thing, okay, is positive charge, for example, so the flux will be coming out, right? Okay, coming out. So the direction of your flux will be in the direction of R if you are using the spherical coordinate system. Then ds again. So you have to decide which ds that you want to use. Okay, if you're choosing the spherical coordinate, so you have to decide, okay, what you want to use. So what you want to use? Look at your Gaussian surface. It is having a 90 degree with the direction of R, right? Right. Am I right? So here you have to choose this one. Okay? No, this one. Okay? So your R here, you should replace it with R square sine theta d theta and d phi, and don't forget the R. It has 2, so you have 2 here, and this Q, you have triple integration, right? Because here it is given the rho v, so v, you have to use this one. Okay? So not enough space, so I will put it here. R square, I think here also not enough. Never mind, I will just put dv first. After that, then I will rewrite it, right? If you have enough space, you can insert this one. Okay, R squared sine theta dr d theta and d phi. Okay? Now, you have to decide the interval. Do you still remember last week we are very confused? Where is the theta? Where is the phi? Okay, how we represent it? So here, mention it again. Okay, so this is the sphere. Okay, so where is the angle of theta? Theta will be an angle started from s-axis and then it move in this way. Okay, so this one will be your angle theta. Okay, so angle phi, sorry, phi. Okay, angle theta will be from here, positive z-axis, and move downward. Which means that your phi will be ranging from 0 to 2 pi, okay? And your theta will be ranging from 0 to pi. Okay? So when we use the spherical coordinate system to locate a point, here they will label the angle and value according to this parameter. Means the first number represent the r, second number represent the theta, and third value represent the phi. In mathematics 3, different, am I right?
Yes.
Mathematics, it represent the r first, after that is phi, after that is theta. Okay? But in max 3, we are not using this one. We are not using this one, and this one. Right? So don't confuse, So I will erase it so that you don't confuse. So in EMT, remember, okay, the angle phi will be started from the x-axis, angle theta started from the z-axis, and the first value r, second value theta, and third value is phi. Okay, so we go back here because here we need to define the interval for the theta and phi. So phi is outside. Okay, it will be from 0 to 2 pi, and the theta is inside, right? So it will be from 0 to pi. So this thing will be equivalent to 1. So you get d r square sine theta d theta d phi. Okay, this one I leave it first, Okay, from here it will become this one. So can you perform the integration? So can you use calculator? Yes, right. Okay, so you can try to perform the integration yourself. I will give you 5 minutes. Take the d and r out, right? Because they are constant. You don't want to integrate both parameters. You can take out them. Okay, only focus on this sine theta. So you will get 2. After that, you will get 2 pi. So I skip the steps, but make sure you know how I get these 2 and 2 pi. Can you get 2 and 2 pi? Yes, right. So it will be equivalent to 4 pi dr square. Okay? You just insert calculator, integrate sine x dx from 0 to pi, then you can get 2. Okay? And this phi, there is no parameter phi here. So when you integrate phi, you will get 2 pi, right? Okay, you try a lot in max 3, Okay, this is what happened on the right, left hand side, left hand side here. Okay, we haven't settled the right hand side. Okay, so now we move on to the right hand side, Right hand side is too long just now. Okay, I don't have enough space to put it. So my rho v is here, and you will have r square sine theta. Okay, you have dr, d theta, and d phi. All these you can refer to the formula sheet. Okay, formula sheet. Is it important for me to arrange this thing in different way? For example, d theta first, dr, and then only d phi. Does it matter? No, You can arrange it according to the arrangement that you like. Can be d phi, d theta, dr. Doesn't matter. So as long as this thing, the interval must be tally. Okay. So now is the r. Okay, the r. So we have to look at the source of the volume charge. So this one will be the source of your volume charge, and its radius is according to the radius of the sphere, right? So it will be from 0 up to R. Okay? And the theta again will be from 0 to pi. Yes. And the other one will be 2 pi. So can you solve this integration? Can you? Try yourself. Okay, so now we put the left hand side terms and also the right hand side term together. Have you forget the left hand side term? This one, right? 4 pi dr square, same as equals to 4 pi over 3 r square r cube and rho v. So what can you do? Here you cancel it. Cancel it is our 2. Cancel, this one become 1. So your D will be R rho V over 3. Okay? So if you want to specify its direction, it is in the R directions. How about the E, the electric field intensity? This is the electric flux density and this is the electric field. Okay? So this one will be equivalent to R rho V over 3 epsilon naught R. Is it the same? Okay, is it same as the slide? Yeah? So how do you use this equation? You have get your equation. So how to use? If I ask you to find the electric field at, for example, this point, so you need to calculate what is the R, the R from the center, So you replace the value here, and then you multiply with the rho v. Okay, the value given for the volume charge density, divide by 3 epsilon naught, and this one as usual, vector r divide magnitude of r, you can get this one. So you can get your E. Okay? Everyone okay on this? Which part you are not clear? Huh? This one or last one? This one. You don't know how this thing become this one? Okay, this one is because the D is equivalent to epsilon naught E. So which means that the E will be equals to D, you divide the epsilon naught, right? So it will be this one. That's why we add this term here. Okay, so normally you can after you get the E or D, you can get the other one automatically by divide or multiply the epsilon naught. Okay, this is their relationship, Okay. Now we move on to the next one. This is when the R, the point where you want to find is electric field, is less than the radius of the sphere. Now we will move on to this case. Can you spot the difference? Just now we are here. Gaussian surface has been moved outside the sphere, right? So which means that now we want to find the electric field outside the sphere. It's not inside the sphere anymore, outside the sphere. So what formula I have to use? I cannot use this formula because it stated that it can be applied only when the R is less than A. So when the R is greater than A, you have to derive a new set of formulation. Do you want to try? Please hide the derivation in the slide. Try out yourself how to derive. Can you? So I will give you 5 minutes or 10 minutes. Can you try? You can draw your sphere first. Okay, so this one is your sphere. You have the rho v, and the radius of the sphere is A. Okay, now you want to find the formula for the electric field. Okay, when the observation point is greater than the radius of the sphere. Right? Okay, you can try. Is it the same as what we have tried just now? Right, same thing, same surface, because our Gaussian surface, it is still a sphere, right? So the angle, okay, the ds that we choose, okay, after the integration, everything, they are the same. Okay, so we proceed to the right hand side. Okay, right hand side. Will it be the same? How about this part? Should I write it as R? A. Do you know why just now I put it as a R, but here I must put it as A? What is the meaning of this Q? Q is the total charge that contained in this sphere, right? Even though your observation point is here, but the total charge actually still depends the radius of A. It does not depends on the radius of R. Am I right? Because it depends on the dimension of this sphere. That's why in this case, okay, this R you have to put it from 0 to A. Okay? But what about the other case just now? Just now we have this one, right? Okay? So when we do the right hand side, where's the right hand side? I put it from 0 to R because my observation point here R is less than the value of A. So if I put my Gaussian surface to be smaller, so the total charge that is enclosed by this Gaussian surface might be lesser, right? So it depends on the value of the R here. But maximum, if you want to find the electric field outside, it can only extend up to A. It cannot go outside or beyond A. That's why here we use R. Okay? So the next case here we use A. You clear? This one is very important, because you will get totally different equations. If you substitute here from 0 to R as well, you will get the same equation like just now. Right? Here you get different equation, so you can integrate, you can solve your integrations. So the rho v sine theta, you take it out, so this one is R cube divide 3. Here will be A, here will be 0 d theta d phi. So here will be rho v, okay, A3 over 3, then you have 2 pi, and you have 2. Okay, check whether you can get this one. Now you put the right hand side and left hand side together. So just now I have d r square 4 pi on the left hand side. Then here I have 4 pi over 3 rho v a3. Okay, so my d would be equivalent to rho v a3 divide r2. Is the same. Okay, 3 rho v. Oh, I left a 3 here. Okay, So if you want to specify its direction, it will be R. And the E, you just top out another rho V, epsilon naught. Sorry. Okay, so this is what the equation that you get. Okay, so we refer back to our slide. Okay, so for different radius, you will have to use different formula. Okay, so you have to decide which formula you want to use. Okay, any question here? You have learned, you have derived for how many times? 5 times, right? Point charge, line charge, surface charge, volume charge when the R is less than A and when the R is greater than A. Okay, so you should be familiar with the derivations. Now I want you to look at this example 15. Okay, 15. Okay, let's read the question together. Can you see it? Make it bigger. Okay, a thin spherical shell of radius A carries a uniform surface charge density ρS. Use the Gauss Law to determine the E at all points. Okay, now you have a thin spherical shell. Okay, thin spherical shell. Can you imagine how does this structure looks like? Spherical shell is in the form of sphere, but it is not a solid sphere. Inside, hollow, nothing. A. Okay, just like what I told you before, you remember the outer layer of Ferrero Rocher? Yeah, that is the shell. Okay, so it has radius A, carries a uniform surface charge density ρS. Given the ρS. Okay, use the Gauss Law to determine E at all points. What does it mean by E at all points? Means, okay, things like that. Okay, you have to find the electric field formulation when the R is less than A and when the R is greater than A. What happened? Okay, that is the meaning of E at all points. Or sometimes they don't use this term, they use E everywhere. So same meaning, means you have to find the E at this region and also this region. Okay, so based on the structure given here, have you tried to derive it in the previous slide? This kind of structure? No, right? So any formula you can use directly? No. Okay, for the surface, what we try is this one. But this is not spherical shell. So what you have to do? You have to re-derive. That's why I let you try so many times. 5 times. So can you try to derive for this one? Can you try? Even though you already know the answer, but can you try? Okay, for the R less than A, why the E is 0? Any idea?
No.
Okay, 10 minutes, let you try this one. I will talk about, okay, so I think all of you got some idea what happened when the R is greater than A, right? Okay, now I want to explain the R less than A first. Less than A first, eh? Because the answer is very easy, right? 0. But why 0? Eh? 0 means you don't need to find, right? But you have to know why it's 0. Am I right? So, okay. So surface says that question says that there is a surface with rho s. Means the rho s positive, right? They didn't give you any value. So we assume here there are positive charges here. Positive charges. So what will be the direction of the flux coming out from the surface? In this direction, right? We call this direction as radial direction. And this radial direction, we often represent it with the unit vector r. So this unit vector r actually represents that this direction is the same as the direction of the radius of this sphere. The meaning. Okay, so what about inside? Do you have any flux line inside? No. That's why when the R is less than A, you don't have flux line here. That's why your electric field is also 0. If the other case, you have a charge here. Okay, negative charge. Okay, this thing might terminate at a negative charge, right? Then you will have flux inside. That is another story. But for this question, because inside there is no charge, so there is no reason this flux line is terminated inside. No charge inside. Am I right? Do you still remember this concept? And the positive charge, okay, the flux line will terminate at a negative charge. Do you still remember this concept? Inside here, there is no negative charge. So the flux line, they won't choose to terminate here because there is nothing here. So here, no flux line and no electric field. This is the reason. Okay? Okay, now we move on to the case when the R is greater than A. When the R is greater than A, okay, give me some time for drawing. Okay, so I construct my Gaussian surface. Okay, in this case, my R is greater than A. So, my Gaussian surface is located outside this sphere. Okay, so this one will be the Gaussian surface, and this one will be the R. Right, and this one will be the A. Okay, so it is always started from this one. Okay. Okay, we go to the left hand side first. So this one, as usual, okay, the flux is in the R directions, and the surface that I choose will be spherical surface, sine theta, and d theta d phi. This is my left hand side. So okay, here. So my interval for the phi will be from 0 to 2 pi, 0 to pi. Okay, so you can do this thing very quickly, right? Almost the same. dr square 2 and then 2 pi. Okay, I settle the left hand side. It is 4 pi dr square. Okay, now we move on to the right hand side, q. Okay, so Q, I know I have to integrate the rho. So in this question, what rho is given? It is not rho v, right? Just now we tried rho v, but here this question is not rho v, but rho s. So meaning here must be ds. Okay, when ds, it means that you will have two symbols of integrations, and the rho s you put here. Now you have to choose what surface you want. Okay, so this is a Gaussian surface. It's a sphere surface. So you should use the spherical coordinate system and you use this one. Okay, same thing. So theta will be from 0 to pi, 0 to 2 pi. So you perform the integration, rho s, okay, right? So this one will become 2 and then 2 pi, 4 pi lah, okay? So it will become 4 pi rho x r square. Okay, r square. In this case, what is the radius of your sphere? A, right? Do you still remember? No matter how big is my sphere, is my Gaussian surface, the total charge, okay, that is represented by my structure actually depend on its radius. It's not depending on the radius of the observation point. Am I right? So in this case, you have to rewrite it, or maybe you put a statement. I will put a statement here. Since the radius of the spherical shell is A, so R is replaced by A. Right? So here means it will become 4 pi rho s and then A square. Any question about this statement? Do you understand? Why sometimes R, why sometimes A? Yeah, because the total charge, okay, here, the total charge, okay, that is within the surface is depending on the radius. Depending on the surface radius. Okay, not depending on the radius of your observation point here. This is your observation point, right? Okay, depend on A. That's why here I have to replace it with A. Now I put the left hand side and right hand side together, 4 pi. And then I have 4 pi rho s A square. So what you do is cancel out rho s A square and then R square. Okay, so this one is your magnitude. If you specify its direction will be R, and your E will be, yes. No, then you will cancel out, right? So different story. Cannot. So this one will be your answer. Okay. So now I will move on to the next questions. B. Question B. This question B is like an extension of question A. Then you can try. You can read it. Okay. If a point charge, like what I mentioned just now, is located at the center of the spherical shell with radius A. We have spherical shell just now here, right? But I insert one more point charge here at the center. Given that the rho s of the surface of the spherical shell is negative 8 microcoulomb per meter square, find the area when the A is equals to 1. When you use this formula, R less than A, R less than A equal, the E is equal to 0. Can you use this one?
Yeah.
No. Why? Because you have one more thing up here, point charge. But can you use this one? Can you?
Yeah.
Yes. Can you try to draw this structure out? We'll do it together for this question. Okay, let's draw this structure out. This is B, label the information inside your drawing. One more informations. 90 coulombs. So now you have a charge here. It's 90 microcoulombs. And A equals to 1. This is your A. Okay? Find the electric field when the A equals to 1. You have to find the electric field. Okay, this is a positive charge. Okay, this is negative charge, right? So E everywhere means you have to find the E when the R is less than A and also R greater than A. Okay, first of all we move to the region where the R is less than A. R is less than A is within this region. So I construct my Gaussian surface. This one is my Gaussian surface. This is a positive charge. Okay? Okay, what happened when the R is less than A? Here you have a negative charge, right? Inside you have a positive charge. So how should I draw the electric flux line here? Positive charge terminate at the negative charge. Am I right? How about this surface? You have negative charge, right? So the other flux line from the positive charge will try to terminate at this surface. Do you agree? So all these charge, all these flux line, they are from the other positive charge outside that we don't know. Okay, it will terminate their electric field line at this surface. So will this line pass through this surface? No, it will terminate here. So which means that inside this region R less than A, there is only electric flux line which is from this point charge. Betul tak? Am I right? Nothing to do with the surface. Only the electric flux line from the positive charge. So in this case, you no need to derive. You can use the formula that you derived previously, this one. This is to find the electric field from point charge, right? This one. So in this case, you can use this formula directly. So this one will be your formula. Q over 4 pi epsilon naught R squared. So can you replace the value into it? Positive 90, So this answer is 808.88. Okay, so this is electric field intensity. If you want to calculate the okay. Okay, so if you want to calculate D, so it will be 7.16 micro R square right. Where the R is greater than A. Okay, now we move on to the second region. R greater than A. So I will use a new drawing here. So okay, let me just simply draw it. So this one is the charge, positive. This is the positive charge here, negative charge outside. Okay, so now I construct the Gaussian surface. So this one is my Gaussian surface outside the sphere. Okay, so this is the electric flux line that I explained before. This is a positive charge, and it will terminate at the spherical shell. Okay. Now we want to find the flux, electric flux density at the region R greater than A. Okay, so of course the D will be contributed by the surface charge density. Am I right? How about this one? Do I need to consider the electric field line due to this positive charge? Or do you think that this flux line will terminate somewhere else outside? Do you think this electric flux line can terminate at somewhere else outside the sphere? No. Okay, so these electric fields, they will stop at the surface of this spherical shell. Nothing going outside. So meaning that outside here is fully depend on this spherical shell. So just now, have you derived the equation for spherical shell? Yes, right. What's your D? D equals to this one, right? Oh, this is E. Okay, never mind. We will calculate for both E and D. So it will be rho S A square divide R square. This one is R square and this one is R. And your E will be with the epsilon naught lah. Okay, you can calculate it. Yes. Okay, so we use this equation. So my D will be rho S. Is it given? -8 micro. Okay, and the A is the radius of the sphere 1 and the r square. Okay, so the answer is negative 8 micro over r square unit vector r. And don't forget is unit. I always forget the unit. Okay, so please make a correction. The slide is not this answer, right? So this is the correct answer. Because okay, the flux line from this point charge, they will stop here. They cannot go beyond this surface. No, now the Gaussian surface is outside.
But still inside the point that is inside the Gaussian surface.
But this field line will not, will not go beyond this surface. So meaning that at this point, you cannot feel the electric field coming out from this point charge. That's why in this region, we only consider the flux line which is due to this surface. This one, it will terminate here and then stop, no more. Okay, meaning that here, if there is no negative charge here, if there is no negative charge on the surface, the electric field intensity at this point will be equals to 0. You cannot feel the force. You cannot feel the electric field because the electric field stops at this surface. Okay? Boleh? Okay. So this is all about the Gauss Law. So I want you to try this one. This is, yes, it's a homework because we don't have enough time to try it here. So same thing. You cannot apply the formula that we have derived previously. So many formulas we have derived, but you don't use it directly for this case. You will have to re-derive. Okay, you can try this thing, then we can discuss it together. Okay? So now it's attendance time.